Hello everybody, my name is Claudia Cecioni. I'm going to present the results of a research activity carried out by the Coastal Engineering Group of Roma University. Professors Franco and Bellotti lead the group, Yuri, Verdiana and Stefano are PhD students. The work is on the roughness factor as overtopping estimator for multi-layered armored breakwaters. Me and Yuri are going to present the new experiments and the analysis of the results. It is well known the rising trend of the sea level. Here we report the two scenarios proposed by the IPCC, which estimates for the near 2100 1 meter of sea level rise in the worst scenario. Given this future scenario, Mori et al. Analyzed the projection of wave heights in different parts of the oceans, estimating a general trend of increasing values of the extremes wave heights. Therefore, the need of adapting the existing breakwater or the building new structures implies increasing costs due to the increasing climate loads. Here we show you also the results obtained by Esteban et al., where the increasing cost percentage for future breakwater is presented versus the water depth. And moving towards shallow water will imply more extreme waves and therefore increasing cost. Burkhardt et al. In 2014 analyzed the feasible upgrade of defense coastal structures to support the increasing loads. And here we report the upgrading options that not imply rising of breakwater crest level. Among all, the front armor solution has been evaluated as the less expensive and therefore the one considered in the present work. Later on, some experimental researchers already investigated on wave interaction with upgrading structures given by adding a front armor, the so-called multi-layer armored breakwaters. In particular, Lee and Cox analyzed the stability of handbars artificial armor units when placed as a front armor to cope with sea level rise. And they found out a damage decrease when there is an extra armor layer. Eldrup et al. Performed also some two-dimensional physical models, testing also the overtopping response of the structures with an extra layers of rocks in the armor. While our research group tested the upgrading solution for an Italian breakwater, obtained by adding an extra tetrapods layer above rocks and tetrapods armor breakwaters. In our previous studies, we analyzed the resulting wave force on the crown wall, while in the present work we is orientated only on the overtopping response of these multi-layer armor breakwaters. Thus, the aim of this presentation is to show you a new experimental test on wave overtopping at multi-layer armor breakwaters and investigate on the role of the roughness factor as overtopping estimator. As well known, the EurOtop manual proposes, among others, a formula that we report here to estimate the mean overtopping discharge given the climate and the breakwater characteristics. The roughness factor, gamma F, is empirically determined for standard armor type. We aim at evaluating the roughness factor for multi-layer armor, in particular an armor type with 3 layers of rocks, or 2 layers of rocks below 2 layers of tetrapods, and 4 layers of tetrapods. The physical models have been built at the wave flume at the engineering department of our university, Roma 3. The flume is 20 meters long, 0.6 meters wide and 1 meter high. It is equipped with a piston-type wave paddle, which have a stroke of 1.35 meter. The generation and the active wave absorption is controlled by the Aalborg University software Avasis, and the incident reflected waves separation is performed following the studies of Eldrup and Andersen. In this presentation, we collect the results of 3 experimental campaigns, here synthetically reported. They already cited one carried out in 2018, where the 48 tests have been carried out on 3 sections, Two of these with armor layers given by 2 layers of rocks plus 2 layers of tetrapods above, and the other one with 4 layers of tetrapods. The 2019 campaign program has been conducted over 3 sections, a standard one with 2 layers of rocks, one other with an extra front layers in rocks for a total of 3 layers of rocks, and the last one with an extra front armor built with 2 layers of tetrapods. The very recent campaign of 2020 consists of 2 sections tested with 2 and 3 layers of rocks. All the 138 tests performed are collected together and analyzed by considering 4 structural layouts that I'm going to describe. We named the section A breakwaters with a armor given by 2 layers of rocks, which collect the results of 2 campaigns for a total of 40 tests. Section B represents a armor with 3 layers of rocks, and it collected the results of 2 experimental programs for a total of 34 tests. Section C is a armor with 2 layers of rocks plus 2 layers of tetrapods above. It collected the results of 2 experimental programs for a total of 26 tests, while Section D is a armor with 4 layers of tetrapods. The results comes from 1 experimental program for a total of 38 tests. The tested wave conditions range are reported in the table. We analyzed the results of all these tests, 138 tests, considering only the response of the structures to the mean in terms of mean overtopping discharge. For all the breakwater tested, we have ensured the armor stability, and the characteristic of the core, filters and armor is similar, as well as the slope of the armor, which is always 1/2. So in order to collect the results of different experimental programs all together, here we present the test results for these 4 sections. So the graph shows the measured mean overtopping discharge over the adimensional freeboard crest, RC over HM0, for the 4 sections. The comparison between different experimental programs, which are given by different colors of the dots, reveals a good agreement of the results.
Good morning, I'm Yuri Pepi and I'm going to present the results in detail. The left plot shows the prediction of the EurOtop formula, and the green dots are the experimental data for section A. On x-axis there is the relative freeboard, and on y-axis the dimensional discharge. Here I explain you the methodology to fit gamma f value from the experimental data. Firstly, for each test, the value of gamma f was varied until the discharge estimated with the EurOtop formula provides the same results of the measured one. Secondly, the roughness factor is then obtained by averaging the single values of each test in order to give equal weight to low and high overtopping discharge tests. To evaluate the goodness of fit, the root mean square error has been used. This methodology has been applied also to the other 3 sections in order to empirically find the roughness factor values for the recently tested multilayer structures. In order to increase the number of data, the clash database has been used. In this database, there are only data related to 1 or 2 armor layers. The data have been filtered as proposed by Bonines and Medina to obtain simple rock armored slope in non-breaking conditions. These have been further filtered by selecting those that were in the same range of relative freeboard and irreparable number as the new tests. At the end, 90 tests were extracted from 2 experimental investigations, one made in Aalborg and one in Edinburgh. Here there is a comparison between the clash data and the new tests carried out in Roma 3. The 2 gamma f values for the 2 datasets are very similar. If we report all the data in one graph, we can see that the results are all in the same cloud. From this point on, when we talk about section A, we will refer to the data of the clash plus Roma 3, for a total of 131 tests. For the sections A, B and C, we show here our experimental data. In all graphs are reported in black the lines, which represent the EurOtop mean overtopping discharge, estimated with the roughness factor calibrated by the data. These results shows that adding an extra layer is a valid option to reduce the overtopping on breakwaters. It's possible to say that the overtopping discharge reduction in these tests is just affected by the roughness factor, because we perform the tests in a wave channel and the test section presents a simple ARMOUR slope, so there isn't the influence of wave direction and the berm presence. However, the tested irreparable number is less than 4, thus excluding influence of long waves. The section D, the one with 4 layers of tetrapods, is here presented together with sections B and C. The calibrated gamma F for section D is 0.40 and the results similar to that of section B, allowing us to conclude that in order to decrease the mean overtopping discharge, is more efficient an extra layer with a larger porosity values. This can be justified because the ability to dissipate energy from the breakwater is given by the discontinuity present within the ARMOUR, that leads to an increase in dispersion phenomena and distortion of trajectories. So, in conclusion, nowadays one of the most challenging problems for engineers is to adapt existing coastal structure to climate change, which leads to sea level rise and increasing wave loads. 138 new tests have been performed on multi-layer breakwater in Roma 3 laboratory, and the preliminary results have been presented. The results for section A with 2 rocks layers have been compared with the existing data of clash, and the founded gamma F of 0.47 results higher than 0.40, which is the one suggested in the EurOtop for this kind of armor. For a simple armor slope, an extra layer is a valid upgrading option. The new tests show a reduction in the gamma F for 15 to 30%, which generates an average reduction in the overtopping discharge up to 90%. However, the tests on the 4 tetrapods layers suggest the importance of porosity and permeability in choosing the most appropriate upgrading solution. Thank you for the attention.